Next, we will discuss how to do integration with parametric equations. And first, we're going to answer the following question. How to find the area between the graph, in this case the graph of a parametric curve, and one of the axes. And first we'll start with the x-axis. And previously we have, when the function is given to us as explicitly as y equals f of x, we answered this question with the following integral. So we integrated on the interval from a to b, and we simply integrated the function. And now what's going to happen when we don't have a function given to us explicitly, but we have it given to us as a parametric curve? So how do we find the area? And the idea is very simple. We are going to, I'm having problems here with zooming, and the idea is very simple. So we're going to take what we used to call substitution, and we're going to replace x with the function of t in this integral, and as in any substitution, we're going to differentiate it, and we're going to end up with this, and we're going to change the limits of integration. So let's say when x is a, the t value is alpha, and when x is b, the t value is beta. And when we do this substitution, we end up with the following integral, which we are going to end up using as our answer to the question above. So we plug in f of x, but f is, so again, let's, instead of f, we're going to just write y here, and we have y of x, but x is of t, so eventually we're going to end up with function y of t, and instead of dx, we're going to have to write here x prime of t dt. And one way that can help you remember this formula is that x prime of t can be written as dx dt, and again it looks like dt's are cancelled. Again, this is not cancellation. This is a theorem that says that those two are equivalent, but it totally looks like dt's can be cancelled, and then you'll end up with exactly the integral on the left hand side. But this is how it's written, and let's do an example. Let's find the area on the one arc of the following cycloid. So the question is, find the area embedded by one arc of this cycloid. So we don't need to draw the picture here because the task is pretty clear, but it wouldn't hurt for us to imagine something like this, right? So we have a cycloid which goes on, and we have, again, this cycloid is a function, but we don't have a explicit form of this function. So we want to know what would be the area of this geometric shape. And according to the formula, we're going to set up an integral like this. And in this integral, we have to identify our alpha and beta. And what is alpha and beta? Alpha is when, so the point is right here, and beta is when point is over there. So these are the values of t that embed one arc, and it should be easy, relatively easy to see that when t is 0, what is x of 0, y of 0? X of 0 is 0, and y of 0 is also 0. And also the value of t that produces this point would be would be 2 pi. Why? Because the parameter represents the degrees of rotation, and x of 2 pi will be what, 4 pi, and y of 2 pi will be 0. So we know the parameters, the initial and terminal value. So we have an integral from 0 to 2 pi. And here we put y function, which is 2 minus 2 cosine t. And we multiply it by the derivative of the x function. So which will be 2 minus 2 cosine t. And is this a coincidence? This could be a special feature of this curve, but I don't think it's just a coincidence that the derivative of y is equal to the x function, and all of this with respect to t. And now we just simply use our integration skills. I'm going to go through this process relatively quick. We're going to factor out 2 and 2, and we're going to distribute the 1 minus cosine t, so we end up with 1 minus 2 cosine t plus cosine squared t. And again, the purpose of this problem is not to teach us how to integrate, so I'm just going to do this quick substitution. Here, instead of cosine squared t, I'm going to write the cosine of 2t and here, what do we have? We have plus 1 over 2. So just use the trig identity here. And again, I'm going to rewrite this one more time. I'm going to take out this 1/2, and I'm going to combine it with this 1. So we have 3/2. And I'm going to distribute the other 1/2 to cosine of 2t. So this is what we have to integrate now. And this should be relatively easy. So we have 4, we have 3/2 t, we have minus 2 sine t, and we have plus 1/4 sine of 2t, and all that from 0 to 2 pi. Most of the things end up being 0 here, which is nice. So we have 3/2 times 2 pi minus 0 plus 0 minus 0, 0, 0. So everything is 0. And the only thing that's not 0 is this. And the answer is 12 pi, whatever the units involved are, squared. So we used this formula to find the area between the graph and the x-axis. Let's discuss another formula. So this time we're going to switch from finding the area between the graph and the x-axis to finding the area between the graph and the y-axis. And usually when that happens, we have a function x, which is a function of y, and basically we just repeat the same exact steps. So remember, this is how we do it with regular calculus. Now we can just substitute everything, and you would imagine everything will turn out being very similar. Just gonna switch up the notation a little bit. So if y is equal to y of t, then dy will be equal to y prime of t dt, and let's just change this to gamma and delta, and there you go. So we're going to have an integral from gamma and delta, and we're going to have y of x of t, which is this function, right? So it's x of y, x of t, y prime t dt, which is very similar to the original. By original, I mean this formula, similar in spirit, and definitely. And let's do this example. We have a parametric equation, a set of parametric equations that define a curve, and we want to find the area between the y-axis and this curve. We can graph it, but I'm pretty sure that the picture will look something like this. We're going to have some sort of graph here that goes from 0 to 2, so it's not a function of y with respect to x, but it is a function of x with respect to y, and we're looking for this area. So we're going to use this formula. The area will be the integral from gamma to delta, and we're going to integrate x of t, y prime of t dt, and we're going to set it up from 0 to 2. X of t is t squared minus 2t, and y prime of t is just 1 over 2 radical t dt. It's a relatively easy integral. Let's distribute 1 over 2 radical t, and let's write it in exponential form. So we're going to have t to the power 3/2 minus, we're going to have just t to the power 1/2. So we have 1/2 t to the power 5/2 over 5/2 minus t to the power 3/2 over 3/2, and all of this we evaluate between 0 and 2. At 0, of course, everything is 0, and at 2, so let's see, we're going to end up with 1/5 2 to the power 5/2 minus 2/3 2 to the power 3/2. And not sure if we can simplify this further, so let's just leave it as is. I guess we can maybe write it as 1/5 square root of 32, but square root of 32 is 4 rad 2, and you can write this as cube root of 8, but cube root of 8 is another 2 rad 2. So I guess we can combine this, but we are getting negative answer for some reason. Of course the answer will be negative because the entire curve is actually below what we consider like below, in this case, will be to the left of the y-axis. Remember, we're integrating with respect to y, not x, so having negative answer is okay. And let's just find the common denominator, which is 15, and do the math. So this is the answer. So next we're going to talk about how to compute the arc length of a parametric curve. And here's the setup. We're going to assume that we have two functions, x and y. And we're going to consider this all happening on some interval between alpha and beta for t. So we have the following picture. At some value t, we are here, and then the parametric curve develops however it wants, and we end up here when t is equal to beta. And in order for us to develop the formula, first of all, let's recall what do we already have. And when the curve is a function, y equals f of x, then the formula for the arc length was this. So we had, this is how we remembered this formula. And what ds stands for? ds stands for the square root of dx squared and dy squared. So symbolically, altogether, this doesn't make sense, this expression, but symbolically we understand that this radical can be rewritten in two different ways. So on one hand, we can kind of, what appears, be pulling out the dx outside of the radical, and then we're going to end up with 1 plus dy dx squared. And in this case, we're going to have to integrate over some domain with respect to x. Alternatively, we can be pulling out the dy from inside of the radical, and then we're going to end up with dx dy squared plus 1, and we're going to be integrating it with respect over some domain with respect to y. So that's how we done the arc length in regular calculus. So the only thing that's going to be done differently when working with equations, parametric equations, is how we interpret the ds. And here's how we're going to interpret ds. Not interpret the ds, I'm sorry, but like what we're going to do with the with this radical. And instead of pulling out dx and dy, again, it does look like we're pulling it out, but in fact this is just an appearance. In reality, it's a theorem that says that these two are the same. But it totally looks like we can throw in and take out dt from this radical, and if we do that, then we end up with a formula like this, and here we're going to have some domain with respect to t. So this is going to be our formula, and let's try to find the let's do an example. In this problem, let's go ahead and find the length of an arc of the cycloid from the first example. So we're going to have the same exact problem, but instead of looking for the area underneath, we're going to find this length right here. And previously we learned that the values of t from 0 to 2 pi generate one arc, and the question is now to find that arc length. So to find the arc length, we're going to use this formula. So we're going to go from alpha to beta, that's the initial and terminal value of t, and we're going to take the derivatives of x and y according to the formula, and basically setting it up as a Pythagorean theorem. So this is what dx and dy here represent. And let's go ahead and do exactly that. Integral from 0 to 2 pi square root. Derivative of x is 2 minus 2 cosine t, and we're gonna square it, plus derivative of y, which will be 2 sine of t squared with respect to t, and we set up an integral. And sometimes in practice we set it up and just run it with some software like Wolfram Alpha or something like that. Here we're going to, I guess, try to do it by hand real quick, just to show you what we can do by hand. Hopefully it's not going to be a hard integral, and I don't think it will be, because cycloids are, maybe they're not nice as an explicit function f of x, but in parametric world they are very nice curves. So let's go ahead and square everything and take out 2, and 2 comes out from the square as 4, but then from the radical it goes back to 2, and we take it outside of the integral. And what we have left is, I'm gonna square the 1 minus cosine t, so it's 1 minus 2 cosine t plus cosine squared t, and here we have plus sine squared t. And this is nice because we have a Pythagorean identity here, so that means we can take out another common factor. However, I'm going to take, it seems like we only have 2 in common, but I'm going to actually take it out as 4. So 4 comes out of the radical as 2, so we have another 2 here. So now we have 4. And remember, here we had 2 minus 2 cosine t, but I took out 4, so now we have 1 minus cosine t over 2 dt, and if we recall the trigonometry here, we probably will recognize this expression. This whole integral now can be rewritten using the trig identity as this, which is nice and easy. Now we simply integrate, and it becomes, the antiderivative of that is, we have negative cosine here, and we evaluate it between 0 and 2 pi. So when we plug in 2 pi, we have 8 over, so negative 8 over cosine of pi, and we subtract, and now we plug in 0, so we have cosine of 0. Well, cosine of pi is negative 1, and cosine of 0 is 1, so we have with 8 plus 8, which is 16. 16 of whatever units are. Isn't that nice? So the length of an arc of cycloid is equal to 16. Who would have thought it would be a nice number? But that's why I said earlier that cycloids are really nice. Finally, let's talk about how to find the surface area of a solid of revolution. So from calculus of regular functions, we remember the following formula. We have it we remembered it this way. So we have 2 pi, and we have an integral over some domain, depending on what type of surface you're dealing with, and what goes inside, we remembered it as r, as a radius, ds. So this formula has different interpretations depending on the setup. So if you have a graph of some function f of x and you rotate it around the x-axis, then the surface area would be interpreted. So in this case, r would be, this is our r, and it will be as the y value. And the surface area formula was then an integral from a to b. 2 pi can be written inside, it doesn't really matter, and r is y, and ds, again, ds we interpret the same way we interpret it in arc length formula. So I can either use one or another interpretation here when computing it for, like, depending on my setup. So it actually was interesting that for surface areas, there were multiple ways to write an integral for computing the surface area. And when we had the rotation around the y-axis, so when we had something like this, and then we take this curve, and then we rotate it around the y-axis, like this, then r, the radius of rotation, was x, and then we set up the surface area as an integral from c to d, for example, 2 pi x ds, and then again, depending on the setup, we can write ds either this way or this way. Now, the question is, what do we do when we have a parametric curve instead of the explicit function? Well, you probably can guess it now. Then we're just gonna rewrite ds according to this interpretation right here, and that's exactly what we're gonna do. So the formula, the short formula, remains the same for parametric curves. The only thing that changes is our interpretation of ds and what r is. But in each of the specific cases, we're going to have the following like expressions. Here we're going to have an integral from alpha to beta, 2 pi, and we're going to have y of t, and here we're going to have an integral x prime of t squared plus y prime of t squared dt. And in this case, we're going to have the following expression. Let's make it from gamma to delta. We're going to have x of t and this. So it's pretty straightforward, or as expected at least. So let's do an example. Let's, for example, find the surface area of a solid obtained by rotating this parametric curve around the x-axis on the interval like this. So we're rotating around the x-axis. Of course, I don't know the details of what the graph looks like, but for the sake of just understanding what's going on here, we can pretend it looks like this, and then we're rotating it on the interval from 0 to 1, around the x-axis, and the surface area that we're interested in is this one right here, all the way around. So that's what we're looking for. And according to the formula that we just discussed, we're going to set it up as the integral from alpha to beta, and the radius here is just the y value, so it's going to be y of t square root of x prime of t squared plus y prime of t squared dt. And now we're going to plug everything in. So the t is from 0 to 1, y of t is 3t squared, and x prime of t is simply 3 minus 3t squared, and all that with square, and y prime of t is 6t, and we also square that. And now we have to integrate it. So a lot of times when technology is available, we'll just throw it into the calculator. But in this lesson, I'm just going to do it by hand. So let's take out 3 and let's focus on the radical. So inside of the radical we have 9 minus it's going to be 18t squared plus 9t to the 4 plus 36t squared. Put this back to t and continuing. So we're going to have 6 pi integral from 0 to 1, and inside of the radical here's we're going to do two things here. We're going to factor out 9, and it's going to come out as 3. So I'm going to take another 3 outside. So 6 times 3 is 18. And at the same time, I'm going to combine the like terms, and negative 18t squared plus 36t squared, before I take out 9, will be equal to plus 18t squared. And after I take out 9, it's going to be plus 2t squared plus t to the 4. And what we recognize inside of the radical is the perfect square of 1 plus t squared squared. And the square root of something squared leaves us with the absolute value. But in this case, the absolute value of 1 plus t squared is redundant, because 1 plus t squared is always positive, so there's no need to write the absolute value around it. And finally, we get a very simple integral, and we're going to distribute t and integrate. Plugging in 1 gives us 18 times 1/3 plus 1/5. Plugging in 0 gives us 0, so there is nothing to subtract, and I just realized that I lost pi. So we have 18 pi here. So doing adding two fractions gives us what, 8/15, and we can simplify it a little further by, we can reduce everything by 3. So this is 6, this is 5, so we get 48 pi over 5. And this is what the surface area equal to of the solid obtained by revolving a given parametric curve around the x-axis. So altogether we discussed how to find the area between the graph and the x-axis, how to find the area between the graph and the y-axis, how to find the arc length, how to find the surface area of a solid of revolution. So in general, we discuss how to use integration with parametric curves.